Um, oh, okay. Is this on? Can you guys hear me okay? Okay. Um, it's my pleasure to welcome you all to the Lunar and Planetary Laboratory here and to our first of the fall lecture series. And we're quite excited. It's very timely, this particular topic that we're going to be talking about tonight, because almost a month ago to the day, a spacecraft was launched, and the speaker will tell us all about it. A spacecraft was launched, and it's currently en route to its destination, and we'll hear all about that. I won't give away steal any of the thunder about what the object is and any details about the launch or where it is right now. I do want to say that there's probably some students here that are receiving extra credit. If that's the case, there's the sign-up sheet is outside, so that's after the lecture. So that's the message I would give to you. Just the sign up things are outside. Okay, so our speaker I would like to introduce. I believe he is actually born in the great state of Iowa. Is that correct? He went to undergraduate college in Iowa at a small college in upstate Iowa called Luther College. Is anybody familiar with Luther College? You have one person. That's a plant right there. Anybody else? Has anybody heard of Luther College? No. It's an excellent school. He then went to the University of Iowa with a long tradition in the kind of research that our speaker does. In fact, maybe some have heard of the Van Allen radiation belts. These radiation belts surrounding the Earth, they were discovered by James Van Allen, who I think basically was a founding father of that group at the University of Iowa, where our speaker went to do his graduate work, received a PhD. His work was so accomplished that he received a fellowship from the National Science Foundation. He then got to pick where he could go after. That provides funds where he could go where he chose, and he decided to go to the University of New Hampshire to hone his skills even further, where he was for a couple of years. And then after that to the University of Michigan, where he was for a couple of years, and then we nabbed him. Okay, and we're very excited that he's here. He's just joined our faculty about a month ago. In fact, I think he started shortly after the launch. Right? Yep. So we're very excited to have him. He's also, in addition to the fellowship, the National Science Foundation Fellowship, but I should also point out he was selected also to win the NASA Living with a Star Jack Eddy Fellowship. That's a bit of a Tucson connection. I don't know if you knew that, but Jack Eddy is, I don't know if people are familiar with Jack Eddy, but he was an astronomer at the National Solar Observatory for many years, right across the street over here. I had many conversations with Jack through the years. He was very, very interesting man to talk to, and a very, very good scientist. And he was the one that made the connection between the sun and climate on Earth. Well, made some of those connections. I mean, a lot of those connections were made a long time ago, but he put a lot of effort into making that connection. And when he passed away, NASA honored him by having a fellowship in his name that our speaker is the recipient of. So it is my privilege to introduce our speaker, Professor Kris Klein, from the University of Arizona right now. So,
thank you very much. So thank you very much for that introduction. I'm going to be talking about a mission that, as Joe said, was launched, I'll find the appropriate height for this, just about a month ago, specifically Parker Solar Probe. And hopefully by the end of the talk, you'll have enough context for knowing why this technical feat is not just something that is exciting because it was hard to do, but will help us understand better the connection between the sun, the Earth, and the rest of the solar system. Just to provide a bit of context, this is the trajectory of Parker Solar Probe. The red dot here over its 6.5-year prime mission. This is effectively in the ecliptic planes, the plane that all the planets orbit around the sun in. The other inner planets seen on here, Earth, Venus and Mercury. We can see them moving around. And the way we're going to get probes so close to the sun is by using gravity assists, effectively the same way that we were able to get probes, specifically the Voyager probes, out to the outer planets, except this time we're giving energy to Venus so that we can fall closer and closer to the sun. So we're going to have a total of 7 different gravity assists with Venus, which will allow us to get to within 4 million miles of the sun's surface. So the question then is, why do we want to do this? Why do we want to, for the first time, measure near the sun? Well, the answer to that is, up to now, we've been having effectively just remote observations, either telescopes here on Earth or telescopes that we've put very near Earth on spacecraft. And those have given us a tremendous amount of information. They've given us images like this. This is actually a combination of 2 different images, specifically one of the surface of the sun, what we call the photosphere, which is the nice circle that we see when we look up in the sky at all times. But it's also this extended atmosphere out here, which is actually much dimmer than the photosphere, and most of the time we can't see that. Effectively, to get this, the extended atmosphere, the corona, to be able to see that, you have to put some sort of block in front of the surface. You have to eclipse it. Now, obviously, we can do that with technology, with our telescopes, when we put spacecraft up there. It was a little more difficult to do hundreds and very difficult to do 1,000 years ago. However, thankfully, we had natural phenomena that allowed us to see this extended atmosphere, specifically eclipses. And so because of these kinds of natural phenomena, we've been able to study the structure of the extended atmosphere for not only hundreds but thousands of years. Going back to, say, the first century of the Common Era, Plutarch notes that when the moon passes in front of the sun, you still see not a complete blackout, but you still see some dim light, some structure, some striation around that that disk. This here is a image from a French painter in the court of Catherine de' Medici. Earlier in 1571, there was an eclipse. People were quite excited about it, and so they decided to memorialize it with this kind of painting. This is something that people were able to, first of all, predict when eclipses would happen, and then start to understand that it's not a perfect ball, but it's some sort of a ball with an extended structure around it. Now, we can still use these eclipses to get understanding of our sun, right? The total eclipse, whose path of totality crossed across the country last year, gave us a lot of not only wonderful photo opportunities, but also a lot of good insight into the structure of this atmosphere. This is from the first point in the United States, in Oregon, the Oregon Museum of Science. They took this wonderful picture, but at the same time, people were building numerical simulations for what exactly this atmosphere should look like, and then compared it to what we were able to see when the moon passed across, occulted the surface, and gave us a picture of that actual surface. And we did indeed see the type of structure we expected. So from ancient times, we knew that there was some sort of extended atmosphere. But we also were able to know that this was not a static thing. It was something that was dynamic, that changed, and changed with great frequency. One of the easiest ways to do that was to look at the sun and count its spots. This is a modern image of a sunspot taken by the SDO imager. Sunspots are dark places on the sun. For up until recent times, we didn't exactly know what were causing them. We now know it's effectively the magnetic field is increased, which leads that particular spot to be cooler. But even without knowing the phenomenon driving them, we were able to count them. And then we started averaging the number of spots over days, over weeks, over months, and over years. And in doing so, we were able to get a better understanding of the actual dynamics of the sun. This is a historic plot of the number of sunspots as a function of time. This is a 13-month average running for the last 250 years. And what's the first really striking thing we see here? We see that there is a very regular pattern. This is an 11-year pattern. It's known as the solar cycle, and we see that it hasn't just happened since the dawn of the space age in the 1950s, but goes back to the 1900s, the 1800s, and even further back. We have other people have counted the sunspots in centuries before this, and this pattern goes back as far as we have historical records for it. But importantly, it's not a perfect sine wave. It's not a perfect wave that has the same maximum value and same minimum value. There's clearly some variation. Right here in the 1800s, this is known as the Dalton minimum, where you actually had not a very robust maximum. You had very few sunspots each year. Recently, in the 1950s, there was an incredibly strong maximum. In the modern era, we've actually been having more extended minima. We've been having less active suns. And so understanding this dynamic behavior is something that's driving a lot of the science that we're interested in doing. And so a lot of that can be done by remote observations, but a lot of it we need to go closer to the sun to actually measure its structure more carefully. Now, in trying to understand the connection between the sun and the Earth itself, let's go to 1859. This is a sunspot, obviously not recorded with a camera, but rather drawn by an astronomer with the last name of Carrington. He was looking at this particular spot and just so happened to be looking at exactly the right time that he didn't just see a spot, but rather actually saw very incredibly bright flares. It lasted for a very short period of time, and in his words, it was as bright as another star. This is another astronomer who was looking at the same spot at that time, Hodgson, and I'll just point out that the appearance surprised him. It lasted for 5 minutes, and it was brighter than the sun's surface. So there was a very dynamic event occurring. This was on September 1st. 3 days later, a plethora of different phenomena occurred on Earth. One of them was the aurora borealis. We didn't have a relatively weak show like we sometimes see. We had an incredibly strong set of lights. These aurora, these northern lights, were strong enough that people were able to read by them in Boston at midnight. This is reported by the New York Times in again, 1859. So this was not just a little dim set of lights. This was something incredibly bright. Additionally, we had a new set of technology at that time, telegraph wires. Those were strung across the country and across the world. In this paragraph we see, they were stringing telegraph wires. These telegraphs were not attached to batteries, and yet they were still working because something was causing them to operate. Some phenomena, which as Times reporter later on this column said, is likely due to electricity, but everyone seems to be blaming electricity, and so that's just clearly the answer they're giving. We do know now that indeed it was a induced electric field due to a significantly and quickly changing magnetic field that was associated with this flare and its coronal mass ejection. But at that time, it was not exactly clear what was happening, but we knew that there was a flare that occurred. 3 days later, there was this dynamic activity happening on the Earth. And so people were really interested in understanding how is the sun's behavior moving into its atmosphere, and how has that been affecting the Earth itself. We also had other ways of understanding the sun's extended atmosphere, again, just by measuring remotely here at Earth. And the easiest way to, that particular way, was looking at the structure of comets. So this is now in the early 1900s, in particular the daylight comet of 1910, which, as a small aside, occurred in the same year that people were expecting the Halley's Comet to arise. So there was actually a bit of confusion. This appeared a few months earlier than Halley's Comet. People thought maybe, the previous 76-year cycle was slightly miscalculated, but then Halley's Comet showed up a few months later, and the confusion was abated. But in this daylight comet, as comets get closer and closer to the sun, their tails become more and more pronounced, and in fact they start to form multiple tails, both a dust tail and an ion tail. Now, the interesting thing is these tails don't fall behind the comet, but rather they point away from the sun. And some physicists at the time did some math, and they determined that the amount of pressure in order to actually push this ion tail away from the comet couldn't be supplied just by the light itself. So the sun, as we all know, is a great source of light, but Eddington and others in the early 1900s said that light is not sufficient to create this ion tail, but rather there has to be, in his words, some swarm of ions proceeding from the sun. And so the question is, what is actually going to lead to this swarm of ions being kicked off? Now, before we go into the details, I need to take a quick aside and review the basic states of matter with you so we can have an understanding of what a plasma is. Now, I think we all probably remember our three common states of matter, right? We have our solids. Prototypically, we have water. All the atoms are bound together very rigidly, and everything stays in one place. But if, we live in Tucson, we put this outside, heat is added to it, what happens? It turns into water. Now, importantly, even though it's not nearly as rigid as the ice is, there is still some cohesion between each of the molecules. That's what gives you surface tension of the water. However, the water is going to fill the container that you put it in. It's no longer rigid in the same way ice is. Let's keep adding energy to it, and eventually it's going to transition from a liquid to a gas. In doing so, you get your steam. There's even less of a connection between the atoms now. You no longer have that cohesion between atoms, and you have just this gas that will completely fill your volume. But what happens if you keep adding energy? What's actually going to happen to those atoms? That's when you move to a new state of matter, something called a plasma. Effectively, the atom itself, which is a positively charged core surrounded by a cloud of negatively charged atoms, is actually ripped apart when you add enough energy to it. The electrons are ripped off of it, and you have positively charged ions and then negatively charged electrons that are actually moving free from one another. So in this very high energy state, you not only are you free-flowing like a gas, but you're actually creating and responding to electric and magnetic fields. This means that you have a whole bunch of other phenomena. You still have a lot of the gas phenomena that you see, but you have a whole bunch of other phenomena that arise in this particular state of matter. Now, these aren't incredibly common on Earth, right? We don't just see a plasma as we walk in the same way that we see solids, liquids, and gases. We occasionally see them in the case of lightning, where you have a tremendous amount of energy being dumped into a very small channel. And we can also use them for industrial purposes, right? If you want to make a plasma television, if you need to do different types of industrial etching, you can use a plasma. They're very rare here, but in the rest of the universe, they're everywhere. They're ubiquitous. Of the parts of the universe we can actually see, over 99% of it is a plasma. Most of that's contained in our sun and all of the other stars that are out there. It's also most of the matter that's, say, falling onto a black hole, and it's an accretion disk. All of the protoplanetary nebulas are typically in plasma states. And the space in between all the stars is filled by a very low density, but still an ionized plasma. And so this means that if we're able to understand plasmas locally, that is, if we can send a spacecraft to measure them at our sun or near the Earth, we can get better understanding of phenomena that drive the behavior across the entire universe. So measuring plasmas is neat, but it's also useful for understanding important processes all around us. So that caveat aside, how do we answer the question of where exactly this swarm of ions is driven by? To do that, we need to move forward a few more decades and go to a physicist at the University of Chicago named Eugene Parker. What he suggested was that the sun itself was not in a static equilibrium. That is, the sun is heavy, there's mass there. It had been effectively proposed that the gravity was enough that everything would remain confined. He instead proposed it's too hot, there's too much of a pressure, and that pressure isn't going to allow a static equilibrium, allowing the gravity to keep everything bound in. And so he built a model that balanced the outward pressure of the hot plasma and the inward pressure of the gravity, and came up with a set of solutions for what the plasma should look like in this new type of equilibrium. I promised I would not show a plethora of equations, and so I will instead just show the solutions to this model, which is shown in this figure at the right. Just to guide you, the x-axis here is just the distance away from the sun's surface, and the y-axis is the velocity of a particular parcel of plasma. The set of differential equations, which is the type of model that he produced, requires that you effectively have a solution that exists on one of these streamlines. Some of them are unphysical. This is the case of 1 and 3, and in the case, 1 and 2. And in the case of 3 and 4, they didn't conform to our understanding of how of basically our measurements of exactly how a plasma on a sun should work. So really the only physical solution was this solution number 5. And just to help you understand physically what this line means, this means you have a parcel of plasma at the sun's surface that isn't moving. Then, because there's enough pressure at the base, that parcel of plasma is accelerated and starts going faster and faster until at this point right here, it goes from being slower than the sound speed to being faster than the sound speed. So it's accelerated to a supersonic speed and then continues being accelerated as it goes further and further from the sun's surface. So this is what his model said this is what the extended atmosphere should look like. There was one difficulty with this. In 1958, no one had observed a supersonic, hundreds of miles per second plasma flowing past the Earth. And so there was many in the community that were quite suspicious of this actually being physical. When it was sent in for review, they said, clearly you've missed something in the math. Clearly there's something wrong here. So for a few years, this particular model was in doubt. However, we happen to be, at this point in time, starting to send spacecraft out of the Earth's influence and being able to measure for the first time in the interplanetary space. And in doing so, we were able to test whether or not this solar wind was actually present. And so there was 2 different missions, one of them accidentally and one of them slightly more intentionally, that were able to confirm that indeed the solar wind was being accelerated to speeds comparable with Parker's predictions. The first one was a Soviet a mission. It was intended as a lunar impactor. The basic idea is they wanted to shoot it and hit it directly on the moon so they could see what kind of dust would be coming up. The rockets were actually a little too good. They were better than they expected, and it missed the moon. They renamed it and said now it's a cosmic explorer. But they were able to measure proton currents and were able to show that indeed there is a plasma that's floating out there, and were able to report for the first time plasma in this interplanetary space. 2 years later, another mission that was being sent to Venus, Mariner 2, was able to measure not only that there was a plasma, but specifically what the plasma's velocity was. And they found that it was in rough agreement with the expectations from Parker's model, and therefore were able to show that for the first time, there indeed was a solar wind. This particular paper the first author was Marcia Neugebauer, who is an affiliate here at the University of Arizona. So we now had for the first time a model that explained how you have this extended solar atmosphere, and then evidence that indeed this model was at least to first order was correct. So what are the implications of having this solar wind that's being pushed off of the sun's surface? Well, you have formation of what we call colloquially a ballerina's skirt. Not only is the sun being pushed off, but the sun is rotating, which means the solar wind moves out and then starts sweeping around in what's known as the Parker spiral. And so this continually radially outflowing, but also continually twirling set of plasma. So you have the charged particles and the associated electric and magnetic fields, fills the entire solar system. But as you get further away from the sun, the pressure in this plasma decreases and decreases and decreases, which means at some point in time, it's going to hit interstellar space. There is stuff out there, it's lower density, but eventually it's going to be the same density, the same pressure as the bubble that's being blown by the sun itself. And this is a schematic of one interpretation of what we think that this so-called heliosphere looks like. Effectively, inside this blue bubble here is that which is controlled by the sun's expanding solar wind. Eventually, that starts to run into the interstellar material. It shocks, it slows down to slower than sonic speeds, and then eventually it pauses and actually stops when the interstellar material, when it runs into the interstellar material, and the pressure there is that much stronger. And so we have actually not only been able to predict that this should happen, but our planetary missions, Voyager 1 and Voyager 2, kept going after they visited all of the major outer planets. And Voyager 1 has actually passed outside of the heliosheath and is starting to measure this interstellar plasma for the first time. And we have great hopes that Voyager 2 will be doing something similar in the not-too-distant future. So since Luna, since Mariner, and since Voyager, we've been sending spacecraft up on a almost continual basis. This is a handy chart made by a colleague at the University of Delaware that lists just a few of the different spacecraft that we've sent up there. Now, on the x-axis is distance from the sun. But just to help you, to guide your eye, this is not a linear distance. This is a logarithmic scale, which means when you go from this hash mark here to this hash mark there, you're not stepping a unit of 1, but you're growing a factor of 10. And then from this mark to this mark, you're growing another factor of 10. The reason that we're plotting this on a logarithmic scale is because the distances involved are astronomical. That was not intentional. The distance between the sun and the Earth is 93 million miles. To the edge of the heliopause is a factor of 100 times further than that. So if we want to show that, yes, indeed, we've measured all the way out here, as well as we're hoping to measure much closer to the sun, we have to stretch it out in this logarithmic fashion. You'll notice that a lot of the spacecraft are sitting in about the same place. Stereo, Mariner, ACE, SOHO, Wind, they're all sitting very near the Earth. In fact, these three right here are sitting at something called the Lagrange 1 point, which is the gravitational balance between the sun, which is very massive but far away, and the Earth, which has less mass but is closer. So it's this nice little point where the gravitational pull of both objects is the same. This effectively gives us a solar wind monitor. And those three spacecraft give us a sense of what the space weather is as the sun's atmosphere blows into the Earth. They've all been up there for decades now and have given us good both scientific understanding as well as some situational awareness of this. These three in red are the ones that are hopefully going to give us good insight into what's happening much closer to the sun. You'll notice Helios, which was a joint project between Germany and the United States in the late 70s and early 80s, did go closer to the sun. It went about to the orbit of Mercury. But Parker Solar Probe is going to go much, much closer, and in doing so is going to help us answer many of the questions that we have about exactly how the sun's atmosphere is blown off and the dynamics associated with that acceleration. So despite these decades of observations, we still have a lot of unanswered questions. Those fall into, very broadly, two different categories. What happens on an everyday basis, and what happens in extreme or exceptional events. In terms of the typical behavior, we still have discussions about what parts of the sun do different kinds of solar wind come from. We have coronal holes, we have and other types of interesting dynamic structure, and each of those are associated with different kinds of solar wind. We also want to know exactly how the solar wind changes as it moves away from the sun. That is, Does the temperature drop as one would expect with an expanding gas? Does the magnetic field fall off exactly as you expect? And also, how does this solar wind impact and affect the magnetic fields around different planets? In terms of more extreme events, we'd like to be able to predict when something like the Carrington event will happen. We'd like to predict not only if it will happen, but if it will actually hit Earth. And we'd like to know what type of radiation hazards and other interplanetary issues may arise for people that are perhaps wanting to travel to Mars. Can we forecast, over the next 6 months, we expect there to be a lot of radiation or not a lot of radiation? Can we build those kind of models that will be useful for traveling between worlds? So to focus on one of those questions, the question of how does the solar wind change as a function of distance from the sun's surface, let's focus on something called the coronal heating problem. This here is hopefully a relatively understandable graph which shows what happens when you move away from a campfire. If you're sitting very close to a campfire, it's very warm, and you decide, I need to move away from that. The temperature falls off with distance, so you get further and further away, the cooler and cooler it gets. That makes just good sense, right? Just because we can, we're going to plot that on a logarithmic graph, just to help us understand the plot that follows. But again, as you get further and further away, the temperature drops further and further off. Again, good thermodynamic sense. This is our model for what happens with the temperature as a function of distance from the sun's surface. It's cool for the sun, and then all of a sudden at this transition region, it grows much hotter, 30, 100 times hotter. So the question is, what exactly is driving this temperature inversion? That's the fundamental aspect of what's known as the coronal heating problem. Part of the issue is you do have a change in density that occurs also as a function of radius, but just accounting for the change in density, effectively density drops off with distance, doesn't completely account for why you have this incredible increase in temperature. And so one of the things we need to do is actually go to this region near the sun and measure the plasma there so we can understand what mechanisms are acting to act in what seems to be a quite unnatural fashion, at least from our understanding of thermodynamics here on Earth. Looking at the more extreme events, we can start asking questions about what would happen if a CME, one of those coronal mass ejections being pushed off of the sun, actually hits the Earth. So we move back further in time than the Carrington event to 1989. There was an X-class flare, one of the biggest classes of flares that happened, I believe, on March 13th, 2 or 3 days later. The CME actually struck Earth itself. This gave us, again, very beautiful aurora, not quite enough to read by in Boston, but still they were quite striking. However, it also caused us to lose communication with our weather satellites. It caused us to lose our ability to communicate with each other via radio. And if you remember this particular time, we were at the end of the Cold War, many people were quite worried that this was the other side inventing a new technology and disrupting our signals prior to a nuclear strike. And so this was quite concerning. Additionally, it led to a power blackout in Quebec. The change in the magnetic field was sufficiently strong that it actually led to a disruption of their local power grid. So this is a time trace of the magnetic field. You can see, so this is a function of time. It's relatively static, and then when the CME strikes, it has very large amplitude fluctuations. But compared to what we think the Carrington event was, this was a relatively weak event. So we could imagine if you don't have the technology of the 1980s or the 90s, but rather the technology we have today, and you have a stronger CME striking us, we would have significant problems. If we lose contact with GPS, not only will you not necessarily be able to drive to the coffee shop, but most of the financial exchanges that we have are dependent on the timestamps from GPS satellites. You could potentially have power disruptions that aren't just hours long, perhaps days, weeks, or months long. And so being able to predict when an event is going to happen, if it's going to strike the Earth, and when it's going to strike the Earth is very important. And so understanding the dynamics of the near-Sun environment is necessary to being able to produce those kinds of forecasts. So this leads us to the science objectives that Parker's Solar Probe is going to specifically try to answer. And just as another aside, the call to actually have a mission like this came a month or two before the formation of NASA. So there was a Simpson committee that was actually formed with Simpson and Van Allen, who Joe mentioned earlier, and they called for a list of either 8 or 10 different science objectives that this new agency that was about to be formed should perform. 9 of them have been accomplished, but because of technical and engineering limitations, we've not been able to send a probe to the sun until effectively this decade. And so this is kind of the completion of this call from the late 1950s to really help us understand our solar system. So the top level science objectives are understanding how energy flows from the corona to the wind and then it accelerates the wind off the surface, looking at those structures and dynamics in a way that we can't do remotely, and then looking at the energization of the and acceleration of the highest energy particles, the kinds that are potentially can cause risks for astronauts or other people traveling through interplanetary space. So there's 2 reasons that we're going to be able to answer these kinds of questions. The first is because we're going to have some great instruments, which I'll go into more detail in a second. And the second is because we're going to be looking at a fundamentally new environment. If you hopefully remember that plot of Parker's solution to the transonic solar wind, this is a model that accounts also for the magnetic fields, which we know are embedded in this plasma. And remember how I said plasmas are a complex state of matter? They actually have multiple characteristic sound speeds. What that means is I'm talking to you via sound, which means I'm making a voice, making a sound. My voice then carries to you at the speed of sound. We're living in a gas right now. Plasmas can transmit information at other speeds. You have another speed called the Alfvén speed, which is the speed at which information travels along the magnetic field. It also has a sound speed in there, which is one of the reasons these are fascinating materials to study. But basically, the solar wind is accelerated to supersonic speeds and then to super Alfvénic speeds. And we've only measured the super Alfvénic solar wind. We've only measured outside of this critical trans-Alfvénic and transonic region. Solar Probe is going to be the first mission that actually lets us to measure inside this region and get a sense of what mechanisms are operating in this previously shielded region. So let's actually start talking about the spacecraft itself. A probe is a tremendous effort put together by hundreds of engineers and PIs across probably at least a dozen institutions. This is a nice little flyby image that gives you a sense of the different parts of it. So what we see as it comes back around again is the front of it is this thermal protection system, which I'll detail in a second. It then also has these solar panels that very nicely actually move back behind into the shield, into the shadow of that heat shield, and in doing so prevent the solar panels themselves from burning out as they get closer and closer to the sun. So the Applied Physics Laboratory at Johns Hopkins has integrated all of these instruments together. The thermal protection system is made of this carbon composite foam. It sits on the front of the spacecraft. And importantly, it's always going to stay between the spacecraft and the sun. It itself will get quite hot, 2,000 or so degrees, but because of its structure, everything behind it in its shadow is going to be kept at about room temperature. So almost all the electronics are going to be operating in a relatively mild environment. There's a few caveats to that I'll point out as we move through the instruments itself. So it's important to remember that we can't talk to this probe as it's traveling along, right? The sun is quite far from us. It takes 8 minutes for light to move from the sun to us. So if it gets into a problem, its onboard automated software has to be responsible for ensuring that that shield is always between the sun and the spacecraft. And so not only is the shield itself quite impressive, but the software to ensure that it's always facing in the right direction has been very, very carefully tested. So because the shield always has to face the sun, there's actually two distinct sides of the probe. There's what's known as the ram side. So if the sun's right here, the probe will move around, and the ram side will be moving into the solar wind, and then there'll be the anti-ram side, which is sitting obviously on the opposite side from that. The first set of instruments on this mission is WISPER, or the Wide Field Imager for Solar Probe. This is a remote set of 2 telescopes who will be looking at the overall structure that probe is passing through. So it's a white light imager. It'll get a sample of the dust and the other structure, the large structure, so we know what probe will be sweeping through. Just so you know, the actual 2 cameras are right there on this ram side. We then also have ESIS, or the Integrated Science Investigation of the Sun. This also is a 2-instrument suite, and it's going to be measuring those most energetic particles, the highest energy particles, so that we can not measure them as we do right now at Earth after they've been tangled up by all the magnetic fields and traveled from the sun to where we are right now, but actually measure them very near to the location that they've been accelerated. The PI is at Princeton, but Joe here is a co-investigator on this mission. ESIS is again on the ram side, so it's going to be able to directly measure the solar wind that it's sweeping through. Our ability to measure the electric and magnetic fields are made by the Fields antennas. It's a very originally named suite. As I said, most of the instruments are actually sitting back here behind the heat shield, but the electric field whips we see right here, there's 4 of them in those locations, don't sit behind the heat shield. They can't if they want to be able to make good, accurate electric field measurements. So they had to come up with a very careful niobium composite, and then had to carefully insulate the rest of the spacecraft from these conducting wires. But they've now been deployed out, and they're making great measurements of the electric field as probe is traveling towards the sun. So not only do we have these electric field whips, but we also have magnetic field measurements that are deployed on a boom all the way behind the spacecraft. So by measuring the electric and the magnetic fields, we'll be able to characterize the kinds of fluctuations that are arising as we get closer and closer to the sun and pass through that transalphanic region. Last but certainly not least is SWEEP for the Solar Wind Electrons, Alphas, and Protons instrument. This set of instruments measures the bulk of the plasma. So ESIS measures those really energetic particles. These measure the typical particles, the particles that are traveling not nearly as quickly. But by measuring these, we'll be able to count how many of them, that is, get their density. We'll be able to get a sense of the average speed, and we'll also be able to measure the temperature of this plasma. And as I said, one of the important questions is understanding exactly what that temperature profile is and what's leading to that inversion of the temperature as a function of radial distance. So these instruments, 2 of them are hidden in the shadow of the shield. Span B, and then on the other side, span A. So we're both on the RAM and the anti-RAM side. And then also SPC is peeking over the shield and is again made of this niobium composite that allows it to directly sample the solar wind without being blocked by that heat shield. And I'm a member of the science team for this particular investigation. So between of the 4 instruments, the University of Arizona is relatively well represented. So as we come to the conclusion, I just wanted to show a quick image of the launch so that we could have a sense of the fact that this mission is moving forward. So probe was launched as Joe said, about a month ago on a Delta IV Heavy. It's pretty much the biggest rocket we have. Three liquid-fueled, with two liquid-fueled boosters, and then they had actually two extra stages of solid fuel boosters sitting on top. Just remember, a probe itself is very small. If you remember the size of the Mercury capsules, it's basically enough space for one person to sit inside of it. That's about the size of probe. So we're using this massive rocket because we need it to go incredibly, incredibly quickly so that it can get into an orbital insertion near the sun. By the time probe gets to its closest approach near the sun, it's going to be the fastest object ever made by man. It's going to be traveling 200 kilometers a second. Effectively, it'll be able to pass over the entire continental United States in less than a minute. So this thing is screaming along. It was launched just about a month ago, and right now it is right here. So again, here's Earth, here's Venus, and here's probe with its trajectory. In half a month from now, October 3rd, it will be making its first close approach of Venus. And the engineers were very skeptical of this, but they have now approved leaving the instruments on, if we wish to, as it passes through Venus's magnetosphere. So we may be getting some interesting planetary physics here, which is a entirely another talk. And then about a month after that, on November 6th, it'll be making its first close approach near the sun. And so this is a very fast mission. We're not needing to wait years in order to actually get to our target. And so the data will start coming back midway through December, and we hope to be able to start answering many of those science questions, not in a few years' time, but in a few months' time. So I'd like to entertain any questions you all have.
Thank you. There's a hand up here. 1, 2, 3. Go ahead.
I just understand that heat shield, is it all just radiant temperature that you're being blocked? I mean, is the plasma itself heated?
So one of the issues is the density is relatively low in this environment. So the plasma itself is going to be hundreds of thousands, or if not millions of degrees. But because the density is sufficiently low, because we're moving through the plasma so quickly, the heat shield itself is only going to heat up to that kind of thousands of degrees. Additionally, there is. There's also. We're actually using a water cooler to help radiate away some of the heat that is then impinged on the heat shield.
Okay. But and then has to be back into the plasma, obviously.
Yes, yeah.
So what kind of material is that heat shield?
It's a carbon composite. It's incredibly light foam. It kind of ablates away if you touch it too much. Yeah, and so there's actually some, because the heat shield is right next to these very sensitive instruments, they had to be very careful about installing it at the last minute, making sure when it vibed during launch it wasn't going to shut off and affect the rest of the instruments. But that's all been taken care of.
Okay, I was just curious, how long in each orbit are you going to be out of communication with the probe? Because I'm assuming when you get too close to the sun, it's going to be too much radio interference.
Yes. So we actually don't talk to the probe as it gets further away all that much. And one of the limitations of our ability to do science here is the fact that the space internet is very slow. And so we have these instruments that can make a lot of measurements, but we're only going to be able to bring a small fraction of that back down to Earth. And so the way we're dealing with that is we take survey data, so lower cadence measurements. We look at that and we say, okay, we want to bring back the high cadence measurements of this and this and this. And so the engineers at APL have gone through and discovered, okay, at this time so we're able to talk to it right now because it's relatively close, but as it gets further away, there's specific times that it'll be able to use the Deep Space Network to talk on this band or that band or that band, and this has been planned out for the next 6 years. So that's another reason that it needs to be incredibly autonomous.
How long is the mission intended to last in terms of duration?
So the prime mission, so NASA does a prime mission, then you can apply for extensions, is for 6.5 years. If we get extended past that, there's not going to be any more Venus assists, so we're not going to get any closer than those 4 million miles from the sun's surface. But because the Delta IV Heavy was able to give it a sufficient Delta V, it looks like we're going to have extra fuel than what was originally planned for, so it's possible that it'll be extended beyond that 6.5-year prime mission.
I was just wondering, when you're talking about the states of matter, is there like another layer after plasma, or no? Is that it?
So once you start adding more energy, that's when you start ripping apart the atoms, the neutrons and the protons themselves, and that's the sort of thing that you do in your particle accelerators. So you can get quark gluon plasma sorts of things, and spitting out of those even more fundamental particles. The question then is, what happens when you run those particles into each other, and we don't have the technology or the theory to predict that yet.
Yes, more questions? Yes.
Yeah.
So what holds the position? Is that tail part of the thing, part of the whole orientation of the probe relative to the sun? What keeps it from getting out of skew?
So they have rockets on it. They have, I forget the exact type of fuel that they're using to keep it oriented, but they have a collection of different sensors, as well as to see if there's any sun impinging on places it shouldn't, and if those have light on them, then it tells no, you have to fire the other way. They also have a few. They actually put in a redundant system of that, so there's actually two ways of them determining if that type of sunlight is falling on it. And then I believe they also have some star trackers that know what orientation it should be at each point in the orbit.
I mean, is there anything in the design? It's kind of like I was wondering if the tail, kind of like a kite, right? It helps keep it oriented.
So the density is low enough that we're not really going to get any nice aerodynamic.
Well, it wasn't the
yeah.
air, but I was thinking the solar winds.
You would need to have much larger fins to be able to capture anything from the relatively low density here. Just as a sense of how diffuse this plasma is. The air we're breathing right now has 10 to the 30 particles in every cubic centimeter. Up in the solar wind, we're talking 10, 100. And so it is a very diffuse material up there. And so that's why in your solar sail designs, you have to have very big sails.
This just popped into my head. The thermal protection system.
Mm-hmm.
Is this a newly patented protection system? Question one. Two, if it's really strong and protective, can it not be applied or used down here on Earth in surrounding, say, nuclear power plants to protect citizens living in cities?
So I don't know if it's in patented. I know that APL is very careful about discussing exactly how it's designed. It was designed to exist in space, which means that they put a bit of this material out for a family day for kids to come along and see. By the end of the day, parts of it had scattered over the entire table. So there are likely lessons that the engineers building this have learned in order to build materials for protecting different engineering assets on Earth. But this exact shield would probably not be that useful for the type of objectives you were describing.
Would this shield erode over time if you were saying it kind of comes apart?
I don't know that it's necessarily going to erode in the space environment over time. I honestly can't tell you if it would erode just sitting on a table. That's slightly out of my area of expertise.
May I double question you?
Certainly.
The fuel that you, the talked about having extra fuel. Is this the fuel that you use to orient the
Yes.
jets?
Yeah. The engineers had planned several additional burns to make sure that the trajectory was correct as probe made its path along, and because the original burn from the Delta IV Heavy got us close enough to what they were hoping for, they didn't need to make all of those planned burns.
Okay, there was a question here, and then there, and then way in the back. So we'll do this.
Did you have a plan for, like, is it going to be landing back here, or is it just going to stay out in space?
No, it's going to keep orbiting.
Keep orbiting.
Yeah. So once it gets through its final Venus assist, it's going to keep in that same elliptical pattern, and it's just going to stay there until it runs out of fuel and can no longer keep the thermal protection system between it and the sun. Once it doesn't do that, the electronics are going to start breaking down, and it'll just kind of become let's say, a man-made comet.
Man-made sun-grazing comet. That
Exactly.
will probably eventually erode. Yeah. Okay, there was one here, and then let's go in the back first. And I won't be able to get the microphone to you, unfortunately. But okay, back there first.
What sort of analysis are you going to do as part of your team?
So we're going to be looking at combining the magnetic field data and the thermal plasma data to try to understand exactly how energy is being transported from those magnetic and electric fluctuations into the plasma and then being turned into actual plasma heat. Because if we can actually identify the mechanisms that are enabling that transfer, we'll be able to answer the question about the coronal heating, what's leading to that temperature inversion. And so that's the analysis I'm particularly excited about. But because we have so many different instruments, there's a bevy of different questions that people are interested in attacking. And the data will first be vetted by the people who built the instruments to make sure that it's making sense. And then will be released, I believe, either 6 months or a year after everything's been correctly calibrated. So that means it'll be up on a public website, and anyone interested in looking at this data and trying to work with it will have access to it.
Yes. Can I get this? Okay. Yeah, wait for the microphone, please. That's right. We're being recorded.
How accurate was the model Eugene Parker made back in
1958. So it was a good first model, but there were elements of the physics that weren't included. For instance, it didn't include a magnetic field in it. It only looked at the forces due to gravity and the forces due to the thermal pressure. And so over the last 70 years, people have started adding in magnetic fields, have started adding in it would also assume there's only one dimension. That is, everything was symmetrical, and the only variations were the distance from the sun itself. So people have also started taking into account the fact that the sun is spinning and other sorts of elements. So it was an essential first step, but there's a lot of work that's gone on after that.
I might say there's somebody in our audience, I think, that could directly answer that question. Marcia. Do you want to hand the microphone to Marcia Neugebauer, by the way, folks, was the PI of the instrument on Mariner 2 that went to Venus that measured the solar wind for the very first time.
Well, Parker did remarkably well. Mariner 2 measured a range of velocities from about 300 kilometers a second to about 800 kilometers a second. So you don't take his curve literally. The one big difference between what he predicted and what was observed was the density. He had been familiar with the comet ion tail data, and the man that had worked on that, Ludwig Biermann from Germany, had assumed that the ions from the comet were dragged out by Coulomb forces. And that required a fairly high density. You can observe the zodiacal light, and you can estimate what interplanetary density is. But back then, a lot of the light that we thought, that Parker and Biermann thought came from ions and electrons, really came from dust particles. So his density was too high, but everything else was right on.
Thank you, Marcia. Yeah. Are there other questions? Yes. Here, I can get the microphone to you.
So you had mentioned in one of the Venus flybys we might have an opportunity to get some planetary data from Venus.
Mhm.
Is there going to be any opportunity either in the primary or secondary mission to get information about Mercury?
No, if I should just go back to the first slide here. We never really intersect with Mercury. We never really intersect with Mercury in a way that would allow us for that kind of study. And just with how planetary dynamics work, we're not going to be able to redirect ourselves there. The Messenger mission, which just recently completed, was sent to Mercury and had instrumentation specifically focused on measuring Mercury, and I'm not sure that the instruments on probe would give us that much more insight than Messenger was able to.
Following on to the solar probe, is there going to be a move to monitor the sun from within the orbit of Venus? Or are we going to have to send further?
The European Space Agency, ESA, is working on putting up a complementary mission, a mission known as Solar Orbiter, that's not going to go as close to the sun, but is going to have a lot more, a different set of instrumentation, and is going to be measuring slightly out of the elliptical plane, and will be sitting in an orbit that's not quite as elongated, but will basically be between Venus and Mercury, staring at the sun. So that's slated to fly in the next few years. So.
Okay. Are there any other questions? Nobody seemed to ask the question. Oh, yeah, there's one more. Okay, sorry, one more. We're almost at 8 o'clock, so we'll cut this off soon. Yeah.
Thank you. Okay. Could you move back to the graph of temperature from the sun's surface?
Yes. There we go.
Okay. So if I'm interpreting this correctly, it's cool at the surface of the sun and then it suddenly gets hotter?
Yes.
Can an analogy be drawn between this kind of behavior and a potential energy well?
So what's happening here is that you have the density is falling off, but the temperature is still not changing exactly in the way that you'd expect for a collisional gas to behave as it moves out of a potential well. And so there's some physics involved in the fact that this is a plasma and the fact that it isn't collisional in the way that Marcia mentioned earlier. And so there's a different set of physics responsible for some of this thermodynamics than what we're used to here on Earth.
Thank you.
Okay, I think we'll wrap it up right now. I will take the liberty of asking the very last question if I could. As Professor Klein noted, I'm a co-investigator for the ESIS instrument, and we're measuring high energy charged particles. This talk very nicely started with the history of the Carrington event. What would happen? Here's my question: what would happen if a Carrington event happened as solar probe was at 10 solar radii?
Probably nothing good. I mean that the kind of all of the instruments, the spacecraft itself are radiation hardened, are tuned for traveling in space, but it's really not designed for that level of an extreme in terms of the change of the electric and magnetic fields passing by it. So let's not hope for that in their first few orbits.
Yeah, I would like to see that happen maybe at the end of its lifetime, just before the instruments are off. I would like, hopefully it comes back around and sends data to us on what happened.
That's the difficulty, right? If it gets hit, it's not going to necessarily send the data back. So.
Anyways, okay, well, let's thank our speaker once again.